Okay, in this video we're going to look at another example using the alternative form of the derivative, which is this. And the problem is we want to find f prime of 0 if this is our function right here. Another way to look at it is what is the slope of the tangent line to this curve at 0? Well, before I start any problem, I always like to look at the graph. And here it is. And the first thing you'll notice is that it's this nice smooth S curve. It appears to be defined everywhere. The only suspect place might be at 0. But if you plug 0 into x to the 1/3, or I'm sorry, if you plug 0 in for x, if f is x to the 1/3, you get back 0. So this is a continuous function. It's defined everywhere. And if you just try to imagine what a tangent line looks along this curve, try to picture what that tangent line looks right here. Well, it appears that it might be vertical. It appears that it might go straight up and down. Okay, let's look at another visual here. and this red line represents the tangent line to my curve. My curve here is x to the 1/3. And this represents the slope of my tangent line. So if I wanted to know what is f prime of 1, what is f prime of 1? Well, here my point is at 1. I simply read off my slope, and it looks like it's right around 1/3. If I wanted to know f prime of 0.5, f prime of 0.5 looks like it's right around 0.53. Okay, well, what's the slope of that line at 0, f prime of 0? Well, if we get really close to 0 here, look what happens. My tangent line disappears, and look what it spits out for my slope. It says infinity. Okay, what does that mean? Let's just quickly interpret this. First of all, we know from algebra that a vertical line, doesn't have slope. It's undefined. Its slope is undefined. So the program here is actually doing some things that would actually generate this infinity symbol here. And we're going to see this infinity symbol kind of pop up in our analysis here in a minute. Okay, so based on this visual, based on the calculator, it looks like we have a vertical tangent line here. So let's see what the actual analysis does for us. Let's go ahead and evaluate this limit, assuming that c equals 0. So the limit as x goes to 0. Now remember, I'm using the fact that c equals 0 of f of x minus f of 0. What's f of 0? F of 0 is just 0 over x minus 0. Once again, all I did was wherever I saw c up here, I replaced it with a 0. Okay, so let's go ahead and simplify this a little bit. Obviously, the zeros aren't going to add much. And if you recognize that this power on x is really 1, we can use properties of exponents to simplify that. And we should get 1 over x to the 2/3. Okay, so now you can go ahead and you could try to use direct substitution here. And one thing I want to make clear is that when you use direct substitution here, you actually get 1 over 0. Okay, you actually get an undefined term. This is undefined. Now notice that this does not equal 0 over 0. Remember this was another entity in and of itself. This was our indeterminate form that we sometimes got when we plugged or when we used direct substitution. We're not dealing with this right now. So this actually tells us something. This tells me that this limit is undefined. Okay, what does that mean? That means that f prime of 0 doesn't exist. Okay, or we could just say undefined. In other words, the derivative at 0 doesn't exist. There is no tangent line there. So if there's no tangent line, well, I take that back. There is a tangent line there. It just happens to have an undefined slope. Okay, therefore, if the slope is undefined, the derivative is undefined. Okay, if you look at this just from a limit perspective, when does a limit exist? Well, it exists when the limit from the right agrees with the limit from the left. And if you evaluate this limit from the right hand side and from the left hand side, let me just write it up here real quick. This would be from the left hand side of 1 over x to the 2/3. Well, if I consider these two guys independently, okay, I'm going to do that on my calculator. And I'm going to go to my y editor, and I already have this function plugged in here. So if I turn off my first function, and now I look at my graph, I'm just going to use this graph to help me evaluate the limit graphically. Okay, so as we approach 0 from the right, you'll notice that my limit is going up to positive infinity. And as my limit, as my x value gets close to 0 from the left-hand side, we're also going to infinity. You could confirm that from the table. These first set of values is approaching 0 from the right, and you can see that your y value is blowing up to positive infinity. Notice that 0 is not in the domain of this new function. This new function represents my derivative. Okay, so now let's go back to this, and we saw that this limit, if we were just evaluating this limit, we could say that it's undefined or doesn't exist, or we could be even more specific and say that it's positive infinity. Remember, this is not really a limit, it just tells us how the limit fails. And we saw that from the left-hand side, it's also positive infinity. So I don't care how you look at it. That was just a good exercise at breaking down a limit problem. But I want you to be clear that the tangent line actually exists. Okay, we actually have a tangent line that exists at 0. The problem is its slope doesn't exist. Okay, and if the slope doesn't exist, then our derivative doesn't exist. Okay, so there you have it. One more example illustrating the alternative form of the derivative. Hopefully at least one of those techniques made sense. We'll see you around.